All right, let's look at question number 5 of the 2019 AP Calculus BC exam. I'm solving this for the very first time. I have not looked at the question yet. Solving them in real time so you can hear my real thoughts. So we have a family of functions given by this 1 over x squared minus 2x plus k. I feel that could be partially fractally decomposited for the right value of k. We'll see if we do. All right, find the value of k such that the slope of the line tangent at 0 equals 6. So we need, in part A, we need f prime of 0 to equal 6. To do this derivative, it would be a heck of a lot easier to just bring that up to the top, raise it to the negative 1 power. So f prime of x would be negative 1 times x squared minus 2x plus k to the negative 2, all times the derivative of the inside. And then f prime of 0 would be negative 1 times k to the negative 2 times negative 2. That needs to equal 6, and so that's 2 over k squared is equal to 6. 2 equals 6, k squared, divide by 6, and square root, you get k equals the square root of 1/3. Do they tell you, okay, it does say k is positive. I was initially going to do plus or minus, but they do tell you that find the value of k for k greater than 0, so we don't need to worry about that. K is the square root of 1/3. I bet a lot of people brain farted and said 1/9 on that one, but you do need to square roots to undo the exponent of 2. Excuse me. All right. Question B, for k is equal to negative 8, find the value of 0 to 1 of f of x, which would be 1 over, and here's the partial fractions. I thought we would do this. I thought we would. We're going to need to factor that. Do the partial fraction decompositions. That'd be x plus 2x minus 4. We'll partially fractally decompose it into x plus 2 plus something over x minus 4, and I'm going to use that heavy-handed method, or I guess that's what it's called, where I'll look and see what makes my denominator 0 under a. That would be an x value of negative 2. So I ignore the factor under a and I plug negative 2 into the rest. So I have 1 over negative 2 minus 4, and I get a to be negative 1/6. I plug 4. That makes my denominator under b equal to 0. And when I plug 4 into everything else, I get 1 over 4 plus 2, which is 1/6, so I get a b value of 1/6. And so now I need to do the antiderivative from 0 to 1 of a, which is negative 1/6, over x plus 2, plus b, which is positive 1/6, over x minus 4. I think I'm going to factor out a 1/6, and it would be, the antiderivatives become negative natural log of x plus 2 plus natural log of x minus 4. We'll evaluate that from 0 to 1. And we will get a final answer of 1/6. Negative natural log 1 plus 2 is 3, plus natural log of 1 minus 4 is negative 3, but we're doing the absolute value of that, which would be 3. Oh, wait a minute. That cancels. Look at that. All that minus. I'm going to put another set of brackets there. Plug in 0, you get negative natural log of 2 plus the natural log of 4, and I'm going to stop right there before I hurt myself. And I need to close my final brackets there. Yee, that's ugly. Shrink that up. Give me some room for part C. I lost my bracket. All right, so there's that antiderivative. And part C, for k equals 1, find the value of that integral or show that it diverges. And I'll be, oh goodness, I didn't even think about it. I kicked into autopilot. There are no discontinuities from 0 to 1. I didn't even think about testing for discontinuities. It was kind of nice that they threw the word divergency. Okay, anytime you're doing a definite integral in BC, you have to consider the possibility of infinite behavior somewhere in the function. There are no, the vertical asymptotes are negative 2 and positive 4. The integral from 0 to 1 is safe. In part C, we're going to do the antiderivative from 0 to 1 of this function when k is equal to 1, which would be 1 over x squared minus 2x plus 1. And that denominator factors nicely to 1 over x minus 1 squared. And now we do have a vertical asymptote at 1, and so there is infinite behavior, which means we need to convert this to a limit as t approaches 1. And if I'm going from 0 to 1, I'm on the left side of 1 of the integral from 1 to t of, and I'm going to bring that up, x minus 1 to the negative 2, because when I do the antiderivative of that, it's going to be a power rule, so it'll be x minus 1 to the negative 1 over negative 1. That's going to be negative 1 over x minus 1 from 1 to t. Limit as t approaches 1 from the left. That would be of negative 1 over t minus 1 minus negative 1 over, what did I do? Oh, that's, my lower limit's 0, not 1. Negative 1 over negative 1, and as t approaches 1 from the left, this guy, 1 from the left, this guy is getting huge. That's going towards infinity. And so we get infinity minus 1, which diverges. Diverges negative 1, 1 from the left, the bottom of negative also. Yep, that's good. So that is a divergent. It's to 2. Oh my gosh. Ah, dadgummit. Okay. So I just looked at the problem and realized that it was 0 to 2, not 0 to 1. So because of that, oh geez, okay, let's fix this. Okay, sometimes you just aren't paying attention and you make stupid mistakes, and you're never immune to that, no matter how long you've been doing this. The infinite behavior is at 1, so technically I need to set this up as the integral from 0 to 1. I want to break it up at the improper behavior. My infinite behavior happens at, my infinite behavior happens at 1, so I'm going to split this from 0 to 1 and 1 to 2. And all of that work I did is still good. We're still going to have to do the integral from 0 to 1. I just kind of ignored, just messed up when I wrote down the problem originally. And when I do this part, we found out that that part diverged. And so since a single part of this diverges, the whole thing diverges. I don't need to go in and do the area from 1 to 2, because 0 to 1 we already know diverges. So I just had to go back and tweak my setup just a little bit. Fortunately, I didn't have to erase and redo the whole problem. There we go. Now I'm done.